let us know how your health and situation is going on. Okay.
Okay.
Try to avoid to have troubles.
I'm trying.
What can we do? Life is difficult. Okay, so I start video recording. Okay, so we have the video recording on. You also have the video recording on. Now I should ask to somebody to switch on the video because I would like to talk.
Okay.
Look in the face of somebody. So I heard them. Becky. Okay, very well. Okay. Eden, you are alone this morning. Or the others are in other rooms.
Iwan added me into the group, so I can follow by myself.
Okay, so let us start with the last lecture, logical concept. I mean, the logical concept which we have dealt with in the last lecture. I think this is very important. As I told you, I found this kind of reasonings in the book which my grandfather studied in 1906 for becoming a lawyer. Okay, of course, he was, for a long while he was studying in a seminar. So before he renounced to become a priest, he studied in very good schools. But this is a standard. This was a standard book in Italian high schools in those times. So you should not believe that I am pushing in your mind some very modern mathematical ideas and that this is not suitable for engineers. I don't believe that anybody claims that the mathematics known by the Italian lawyers at the beginning of 20th century is more than what at the beginning of 21st century an engineer should know. By the way, this is a very important logical argument. Many politicians are confusing the logical structure of logical argument. Okay, so imagine that you know that the statement A is true. In our case, the statement A was the inner product of V with itself in the vector space which we have 0 implies that the vector V is 0. Okay. And the proposition B was that the determinant of GAB is different from 0. So I remind you what is GAB. If you have VW inner product, we are talking about a generic inner product in our vector space. Because of linearity, we can write this like VA EA, comma VB EB. Okay, and W, and as we have a multilinearity assumed for the inner product, we have that VA WB EA EB is the formula for our inner product. If we call this if we call this GAB, we have the formula, component-wise formula for the generic inner product, where GAB is symmetric. So when you try to represent G as a matrix, you are sure that independently of your choice of the index for the row and the index for the column, the representative matrix is always the same. Be careful. The choice of row index and column index is not important only for symmetric tensors. Okay? Otherwise, you risk to say something wrong if you are not consistent with your notation. Okay, but you know, A and B could be every statement. Okay, so what we say is that A implies B. Okay, so we know that when we have a bilinear product, a bilinear application verifying the proposition A, then symmetric, then automatically the determinant of GAP is different from 0. So whenever A is true, also B is true. And this is the meaning of this symbol. Okay. Now, I will tell you the same thing as I did last time, but I will give you more details. This means the negation of B. So this is the symbol for meaning that if I have, this means B is not true. Okay, so the statement non-B means that B is not true. Now, Alessandro, who studied some logics, will see that I am mixing semantics with the algorithmic part of logics, which is called also syntax. But you know, this we can do for a while. Okay, you don't need to become an expert in logics, but the most fundamental ideas of logics are essential. By the way, I think that Angela Merkel is being a very clever prime minister simply because she has a PhD in theoretical physics. She's a very logical person. Okay, now, so logics is useful for everybody, not only for engineers, for mathematicians. Okay, now, I want to say that the negation of B, so in our case, telling that this is false implies the negation of A, that is that this is false, if and only if A implies B. So either you prove this implication or you prove this implication, you have the same statement, in the sense that if you prove one dot implication, two dots implication is true, or vice versa. If you prove two dots implication, one dot implication is true. Okay? And it is very easy to prove this using tertium non datur. The third possibility is not given argument. So we accept that a statement either is true or it is false. And you cannot have a third possibility. Many human beings play with truth and falsehood of things as if one could play with this concept. Something is not 20% true and 80% false, or something like that. Even if somebody invented a fuzzy logic. So imagine that non-B is true. Okay? And A is true. So imagine that the negation of B is true and A is true. Both of them are true simultaneously. Okay? And assume this. So assume that A implies B. So as A is true, the implication of B is A implies B, therefore B is true. And so you have that non-B is true and B is true, which is impossible. Okay? So we arrived to a contradiction when we assume that non-B is true and A is true. To avoid the contradiction, non-A must be true. So what we have proven, that if non-B is true, then non-A is true. So we have proven this implication. Okay, so we have proven in another way once more that if this implication is true, then this implication is true. Do you believe that we must prove the vice versa? I don't think so. Why? Because again, the statement of tertium non datur tells you that the negation of B is B. So if I say that it is not true, that something is not true, it means that something is true. Sorry for the game with words, but you know, this equality is obvious. Telling no 2 times means that I'm telling yes. So the other implication, we have proven this implication. The other implication is trivial. It is enough to write that not A implies not B. And use the same argument as we did before. I think that this is the bare minimum of logics which we need. And I hope that I didn't increase your confusion repeating this argument. In case we have discovered this morning that Alessandro had a class in logics for getting his master, so maybe if somebody among you has extra troubles, you can discuss with him, also with me if you like. We should try to fix some hours where we meet outside the lecture fixed periods. Okay, so let's go back to our inner product. So we have the inner product between two vectors in a vector space, and we have discovered that we can represent component-wise this inner product by means of a matrix whose determinant is different from 0. Okay. Okay. Now, this condition, which is called non-singularity of inner product, has obviously a consequence. There is an inverse matrix for GAB. Okay? And this inverse is symmetric. Okay? So, by definition, we write G C D. This is the inverse matrix for GAB. So simply placing the indices up means that we are inverting the matrix. Be careful, because this notation is very important for understanding what we are doing next. We already introduced in one of the first lectures this notation. I'm repeating it to you for being sure that you have understood it. So you can write this formula which defines the inverse matrix. GCA, GAB is equal to delta CB. Okay, where delta is the standard Kronecker delta. Okay, very well. Now we go back to our natural identification between a vector space and its dual. This natural vector space is determined, so we talk about the natural identification as determined by an inner product. Okay. So what we do, if you remember, I remind you that we already identified, we have already proven that the dimension of V star B is equal to the dimension of VB, and that we have associated to the basis EI down, the basis EI top, and EI top is an element of V star B defined in this way. EI applied top, applied the vector V is equal to VI. VI is the component of V in the basis EI. So EI top depends on the basis EI, and indeed EI top is called dual basis for EI down. So we identify a vector, a basis in V star B, which depends on the basis in VB. When you change EI, the E top, E up, I changes. Okay. So when you identify a vector with a covector, telling that the identification of the covector having the same components in EI as V has in EI is an identification depending on the basis. What it means that you change the basis and the covector associated to a certain vector changes. So it is a basis dependent identification. Now, why I repeat this many times? Why an identification basis dependent is not good? Because we want a formalism where it is easy to introduce basis independence. The laws of physics must be formulated in a way that they are independent of the basis. Okay, this is the essence of Galilean invariance. Okay, so we need to have conceptual tools where these basis independence are inbuilt logically inside the theory. Okay. Now, the concept of inner product gives us this basis independence structure. Let us think how. I take a vector V inside VB. Then I consider the following linear application in V star B. The linear application associated to V, calculated in the vector W, this is a real number, is equal to V inner product W using the introduced inner product. Okay. So this is the definition of the isomorphism between VB and V star B. Of course, I must prove that it is an isomorphism. So what I must do, I must prove that the application which associates to VLV is 1-to-1 between VB and V star B. Okay. Okay, first of all, let us prove that it is injective. What it means that an application is injective. I assume that LV1 is equal to LV2. And I will prove that V1 is equal to V2. Okay. Okay. So this is trivial. Now you understand why I spent so much time discussing about non-singularity of inner product. You will see immediately. Because LV1 applied to W for every W has to be equal to LV2 applied to W. Okay? So by definition, V1 W is equal to V2 W. I don't know if you are recognizing the reasoning which we did when we have spoken about deformation. Because then what I write? I write V1 W minus V2 W equal to 0. Then V1 minus V2 W is equal to 0. Okay. And then I write this. This statement means that W, the generic vector in VB, is orthogonal to V1 minus V2. So the generic non-singular inner product is such that the only vector which is orthogonal to every W in VB is the zero vector. So we can say this one, that this equality is true. How should we proceed with algebraic argument? GAB, V1 minus V2A, WB equals 0 for every WB. Okay? And with simple algebra and considering that the determinant of GAB is different from 0, this implies that V1 minus V2A is equal to 0 for every A. Try to reconstruct this. This argument we have repeated several times. So the application is injective. So only one linear map is associated to a vector. Okay. Now, we must prove that it is surjective. So we must prove that for every L belonging to V star B, so for every linear application, there exists a V belonging to VB such that L is equal to LV. Okay. Now I will prove this with a quick argument. So I take V. I represent V in the basis EI. So it is a proof which uses the basis. We can do it because we already know that the map L, the map which associates to every V, LV is independent of the basis. Okay, so we don't need to worry about this anymore. Okay, so I take L having the component I in EI. Okay, let us use another index J. So I define LV as follows. I built the components of LVJ. The components LVJ. So I tell you which are the components. Okay. And the components LVJ are given by G, JI, VI, where this G is the inner product of EJ, EI. So this is what we call the matrix representing the inner product. Okay. So in a sense, mnemonic trick. We are lowering the index. And we are lowering the index by using the matrix, the matrix of inner product. Okay. Now, let us calculate so what we do. We take the generic L. We write it like LIVI, and we ask ourselves, of course, this is wrong. This is a linear combination representing L in the dual basis EI. Okay? Then we say, let us use the same index as we did before. Then we say, look, I want that L is GJI VI EJ. So I want that it is the linear map whose components in the dual basis are obtained by the components of V in the starting basis by lowering the indices. So the components of L are obtained by lowering the index. Okay. Then what I do, I calculate L, and this I call LV. Okay. Now, my problem is, this LV, is it equal to the LV that we have defined. So maybe let us call it L tilde V. So a priori, this V here, this LV here, where it is, this LV here has been defined as V inner product W VB. Okay, so this is the definition of our mapping. Okay, so this is our definition of the natural identification. So here I am making some calculations and I'm introducing another, apparently another linear map inside V star B associated to V, and we have obtained it by lowering the index. Okay. So now I calculate this L tilde V on W. So I use this formula, Gij Vi Ej applied to W. But Ej applied to W, by definition, is Wj. And we discover that this is exactly LV of W. You know, I'm telling you a sequence of trivial, very simple things, one after the other, but I'm trying to prove you every single step. You know, usually students are taught these things with the brutal method. You know, the brutal method is the one which the officer used for my grandfather when he started being a sailor, being 17 years old, many years ago. They pushed him in the water. And in order to survive, he learned how to swim. Okay, so usually all these things are not said systematically to students. And if you are not drawn by the water of tensor algebra, you survive. This, I think, is the main reason for which many think that linear tensor algebra is crazy, something you cannot understand. I am underlining for you, you know, what I had troubles to understand. GHL, GLM is equal to delta HM. This is the inverse of that. So in order to have this fundamental matrix here, you need inner product. Okay. And now, in order to construct V, which corresponds to LV, you need to use the inverse of G. Because Vi is equal to what? Gij LVJ. So if you know the components of LV, then you know the components of the corresponding vector in the one-to-one correspondence. Simply using the Gij matrix with upper indices. Okay, so now I don't know why I'm missing in English, but I use. Okay, no, I remember. So you lift the index. You lift the index. With the inverse matrix. So you lift the index, so you transform the inverse matrix of G, H, A. So, given an inner product, okay? In a specific basis, it is represented by a non-singular basis. So, a singular matrix should stop thinking to what I want to do, say next, and write slowly. Okay? The matrix is this one. It's the one which allows you to write this formula. Okay? Gij allows you to calculate the inner product. By using the components of vectors. Okay? Then lifting the index, one can calculate the components of the covector associated to a given vector. So Vij is equal to Lj. And this Lj we call Lvj. It is the linear map associated to V component J. Okay? Remark, LV is the same covector when you change the basis. Because this depends on the basis. This depends on the basis. this depends on the basis, but the representative linear map is always the same. What I want to say is that LV of W, so the linear, the value, the real number associated to the vector W, at the end of the story does not depend on the basis. So if you write this equal Gij Biwj, this depends on the basis, this depends on the basis, this depends on the basis, but the resultant real number is independent of the basis. Okay, so we have a very nice component-wise representation. A component-wise representation which does not depend on the basis. Okay. So now we can talk about Cartesian tensors. Cartesian tensors are tensors in which a vector is identified with a covector. So I try to explain you slowly. I think that we have time. I wanted to end this tensor algebra basic discussion today, so I think that we can do it, hoping that we will not need extra for proceeding. So now what we have done, to every vector V, we have associated a unique covector LV. Okay. And the identification is independent of the basis. So now we can understand why Lagrange, before also D'Alembert, and then Piola stated that forces are covectors. If you think about it, you cannot measure directly forces. You can measure the effect of forces. So, for instance, you can measure the variation of kinetic energy which is induced by a force. So if you remember, the inner product, let us use the what you have learned already, okay? The inner product of a force times a velocity is equal to the derivative with respect to time to 1/2 the mass V dot okay, the variation of kinetic energy associated to this. So let us write it in the right way. F. I am remembering the mnemonic. This is a mnemonic trick because this is a consequence of our axiomatic. But let us use the standard reasonings you have followed in physics first year. You calculate the inner product of the force and of the mass times acceleration. This is the power expended by the force on the velocity v. And what is this? You have 1/2 mass v dot v time derivative. You assume that the mass is independent of the time, 1/2 comes out. So you have d over dt of v dot v. And 1/2 m, then you have d over dt of the velocity, acceleration, dot v, plus v dot d over dt, velocity, it is acceleration. So at the end, you get 2 times mass acceleration times velocity. This better. This you can measure. Why? Because you shoot a picture of your body in a first position, P1. Then your clock runs, you shoot another picture, P1, okay, P1 and at instant T0. Then P1 at instant T0 plus delta. Then P1 T0 plus 2 delta. And then P1 T0 plus 3 delta. With this increment, you estimate the velocity at the one instant in between T0 and T0 plus delta. With this increment, you measure the velocity at another instant between T0 plus delta, T0 plus 3 delta. So you have this velocity and that velocity. Then you make the difference between these velocities and you divide times the interval between these two measurements and you get the acceleration. Similarly, you know the velocity. What you are doing, you are measuring the, if you like, either this quantity or this quantity with kinematical measurements. Okay, so you are not estimating, you are not measuring a force directly, but only via kinematic measurements and to a theory, or if you want, or if you like, a theoretical definition. Okay. So if the theory is wrong, your force could be totally meaningless. You must understand this. The concept of force is a pure mathematical abstraction. Even if there are many people who try to sell you a force like a practical engineering concept, we will see that this is totally false. In all this course will be dedicated to proving you that the concept of force is very mathematical. This is a very strange situation. Engineers persuaded themselves that force is practical because they could not psychologically accept the idea that they were speaking about something which is not practical. And this is totally misleading. You know, in a sense, a force is like square root of -1. I'm trying to do a very courageous parallelism. You know, in many calculations, the imaginary unit is used as an artificial trick for finding a real number at the end of the story. While every real number is associated to a quantity, a complex number usually is not associated directly to quantities. Okay, it is a mathematical abstraction which is needed if you want to find always n roots for an nth order polynomial. Okay, then some electric engineers invented a way for giving a meaning to complex numbers in the theory of circuits, but this is another story. Okay, so let's go back to our definition. So at the end of the story, when you are talking about the variation of kinetic energy, which is induced by a force, you naturally, this is the inner product Euclidean inner product. So when you introduce the concept of variation of kinetic energy induced by, you know, changing the word, one could say an interaction. But we say that the external world is interacting with your material particle, and this interaction induces a variation of kinetic force. And this variation of kinetic force is a linear map which takes a vector velocity, and to this vector velocity, which is a vector like displacements. Okay, and to this you associate a real number, which is the variation of kinetic energy, because variation of kinetic energy is a real number. This is a real number, even if you are building it with vectors. Okay. So following Lagrange, we introduce vectors, essentially displacements, and covectors. An example is given by forces. Okay. Okay. Now, for our calculations, it is very useful to introduce the vector associated to LF. So we use the identification given by inner product to write this formula. So in a sense, we are identifying the linear map which takes velocity and associates to the velocity a real number, and the vector which via the inner product allows us to represent this linear map. Okay, so one can identify the linear map LFV. Okay, LFV is a real number, so LF with F. Now, it is astonishing when you read the original text by Lagrange and also Piola textbook. It is astonishing how they carefully distinguish between these two concepts and how carefully they repeat systematically that the vector F force represents the power, and in order to make this representation, we need an inner product. Okay, you will see how important is this difference. I want to tell you, you will see how important it is for you to understand that the standard vector you use for talking about a force is a representative of the power linear map. Okay? Okay, now let's quickly talk via an example. Okay, I have time for doing this carefully, slowly. So we have identified a vector with this dual. And the identification is given by this formula in short. And when you have this component-wise representation, LV, lower index J, you write in this way, G, J, I, V, I. Now, you understand that as you have written this, okay, and as EI you started writing with the upper index, it is very how to say, natural, that the laziness will induce you to replace this symbol, LV PEDEX lower index I, with VI. So VI is the covariant set of components of V. And then the process of identification is completed when you write this terrible, I refuse to write on the same line, this terrible sequence of equations, which you find in many books, because you identify V with LV and you write it. So you write vector and covector in the same way. And then you write the components, the contravariant components of V in the basis EI, and the covariant components of V in the basis E lifted I, with I at the top. If you are a poor student and nobody has told you everything, as I tried to tell you, and they only told you that this is a quick way for writing this formula, you will have difficulties in understanding that this other formula is not a pure rewriting of the previous one, changing the order of indices. I mean, you may alone be able to reconstruct that this means that, and this means that. Then the chaos is increased by the fact that many engineers, you know, when I think 15 years ago, I had a group of PhD students who now are all professors. They organized a revolt against me, doing the following crazy reasoning. I want to tell you this because you must understand that there is a delicate conceptual process behind what we did. And I gave all details of this conceptual process. And as usual, only stupidity can require simplifications, which destroy the complexity of your ideas. Now I tell you this. Imagine to have EI orthonormal. So EI inner product EJ is equal to delta IJ. Okay. Then GIJ is delta IJ, is the matrix with 1 in the principal diagonal and 0 outside. GHL is also delta HL. Okay. So actually, E top and E bottom are the same. Okay, maybe this I didn't tell you explicitly. Okay, how can I represent EI in terms of EJ by using the inner product? The formula is this one in general. Let us prove it. So EI, okay, you know, we are discovering that I didn't tell you something. So we will go back to the craziness of orthonormality and the apparent simplification which we produce. Okay, so I represented LV in terms of V. Okay, and I'm teaching you that LVW is equal to V inner product W. This is the identification between vectors and covectors. Okay. Then one could ask, EI, how can I represent EI in terms of EJ if this means sounding, of course. So this identity, I want to underline for you this. This is formally wrong unless you have done this crazy identification. So you have forgotten that LV is a linear map and V is a vector. And you have written V equal VI EI here in this way. So you have identified a vector with the associated linear map. So when I have written this, you should be very upset against me. I don't know if you agree. Why you should be very upset against me? Because this is a covector. And these are vectors. And this is a linear combination of vectors. So this formula should be written until we are very familiar with our process in this way. You understand that this notation can be very clumsy. By the way, you know, sometimes it is very good if I use the principle of authority for, you know, I try to find some good witnesses for explaining you that what I'm telling you is very important. I mean, this confusion most likely has been pushed in the books by Einstein when he wrote his general relativity papers. Okay, so let us do slowly this argument, develop slowly this argument. So what I want to say, when I wrote EI equal GIJ EJ. Actually, I wanted to say that EI is the covector associated to the vector which I've written in this way. Okay. Now, to prove this is rather easy because what we do, EI applied to the vector V has to be equal to L Gij Ej applied to the vector V. This is the definition of two equal linear maps. Okay, this has to be true for every V. This we know. This is VI. Okay, and this is what we know. So Gij Ej inner product V. Okay. Gij are coming out. And we have this formula. Okay. Now, this is exactly L Ej applied to V. Okay. So at the end, we have that this object, which is a linear map associated to this linear combination of vectors, is the covector associated. This is the covector associated to EI top is the covector associated to this vector. Okay. And so this is the confusion. Dangerous is a source of dangerous confusion in our studies. Okay, I think I will come back to this also next lecture, because now I want to go ahead, but please consider that here you have a very bad abuse of notation. Now, let's go back to this formula, which is already confusing by itself. Okay, because by definition, this was a covector and these are vectors. But now, if Gij is equal to delta Ij, this becomes a trivial statement. So, because of this simplification. By the way, Vi is equal to Gij Vj, and Vj is equal to Gji V, the formula of the other, with the abuse of notation. But you know, when you see the upper index, you know that you are talking about a linear map, a vector. And when you see a lower index, you understand that you are talking about a linear map. But if you have that Gij is equal to delta ij, this becomes Vi equal Vi. And this is terrific. And also forbidden by our notation. And similarly, you have Vj equal Vj. So at the end, people decide that we are not interested in the complication of the theory which you are presenting us, and I will use only an orthonormal basis. The final result is that one is confusing vectors, so displacements, with covectors, which are forces in our theories. And one believes that they are the same mathematical object. I mean, they belong to the same structure. They have the same properties. In particular, that they change in the same way when you change the basis. And this is extremely confusing. So even if my teachers told me that one should avoid making this example until the very end, eventually using complicated symbols for making distinction between these two, you know, in general, in good books, you find equations like this one. However, I think it is essential for you to give a motivation against this oversimplification, because people very often hear comments like, this theory is a mathematical depravation, and people using tensor algebra have a serious mental disorder because everything is simple. It is enough that you use orthonormal basis. Okay, I think that if you do this simplification, you lose the possibility, you will see also in the next lectures, you lose to make a clever distinction between different mathematical objects, and this distinction is reflecting the difference between physical entities. Okay, so let's try to end dealing with a generic, did identify a vector and a covector using contravariant and covariant components. So one vector one vector and its associated covector have either contravariant components or covariant components. Okay, so in our identification, once you have identified one vector with its associated covector, I will not stop repeating that by means the association is obtained by means of an inner product. Okay. When you have done this association, then one entity, the vector covector, one should call it with a specific name, so we call it Cartesian vector, for meaning that we intend one vector and its friend, the associated covector. Okay, is characterized by contravariant or covariant components. Okay, now let us consider a generic tensor. So let us start with a simple one, Lij. You remember, a linear map between VB and VB we have represented with its components. So L, here, of course, I have W. L of V is W. Okay. And as you remember, L VI EI is equal to VI LEI. LEI is represented in the same basis, EI, via linear combination. So you get L I VI J EJ. Okay. So W is represented as follows: L J I V I E J. So WJ is L J I V I. This is a vector. This is a vector. So LJI verifies the criterion of tensoriality. So it is a tensor. Following Landau definition. It is a tensor because it is a linear map between vector spaces following the definition of mathematicians. Okay. Now, what happens if instead of writing V like VI, EI, I represent V like VI, EI at the top with this horrible abuse of notation. I will repeat that we are doing an horrible abuse of notation for a lot of times until you learn that you must, these are covectors. You have a linear combination of covectors. So this is a covector. Here you have vectors. This is a linear combination of vectors. And this is a vector. So, in a sense, let us try to relax a little bit. It is like Dr. Jekyll and Mr. Hyde. You have a schizophrenical behavior of a Cartesian vector. Sometimes it is a vector, sometimes it is a covector, depending on how you are representing it. Okay? And you have an identification. The identification is obtained via the inner product. So VI is equal GIJ VJ, or VJ is equal G, sorry. Now you know how important is the placement of the index. Okay. Okay. So L, I must be very careful. Instead of writing L of VIEI, now I will write L VJEJ. So here there is the covector instead of the vector. Okay. So I write this VJ EJ. Sorry, LEJ. Okay, how do we want to represent this? Because LEJ can be a vector or a covector, depending on how we want to represent it. Is it Dr. Jekyll or it is Mr. Hyde? I prefer to call Dr. Jekyll the vectors and Mr. Hyde the covectors for the reason which I told you. Because for me, forces are not understandable by human mind, while displacement, yes. So Dr. Jekyll are the vectors and Mr. Hyde are the covectors. Okay, so let us start representing LEJ as a covector. So I want to represent it in terms of EI at the top. So I write L, J, I. Okay. So LV is equal to VJ, LJI, EI. Okay. And I must represent use this. So W is given better. Now let's go back and copy this other formula and write it here. Now you can remark that here the saturation is built with the upper index of L, while here the saturation is built with the lower index I. Okay, so what we are doing, we are writing at the top formula, we write Wi equal Ljivj. This is the representation there. While here we write Wj equal Ljivj. So we have discovered that saturating the contravariant index of L with the covariant index of V, you get the covariant index for W, or saturating the covariant index of L with the contravariant index of V, you get the contravariant index for W. Okay? We are happy because we are starting to prove that upper and lower index saturation is perfectly compatible with our identification. We know it because we invented it for getting this. Okay, now instead of representing, let us go back here. So I rewrite this formula. So LV equal VJLEJ. Okay. Now, this is, we represented this how? In the basis with the upper index. Okay, so let us write in this way. As we did. Instead of doing this, I want to identify this with the lower index. So instead of writing this, I write E, H, G, H, I. Okay, it's more elegant if I write G, I, H. So I am representing EI in terms of lower indices vectors. So here we have an abuse of notation because we are identifying a vector with its associated covector. And we have the formula L, J, I, G, I, H, E, H, V, J. Okay. So our W has now the component H given by this formula L, I, J, G, I, H, V, J, E, H. No, E, H is dead now. So what we discovered that L, J, H given by L, J, I, G, I, H is the associated 2 times contravariant tensor to L, J, I. So L, J, H saturated with Vj gives you WH. So this maps covariant components of V into contravariant components of W. So what we have understood that the linear map L, the one from which we started, this one, L maps VB into VB. However, you can take L of V, it can be represented in this way. Contravariant. Or it can be represented covariant. Okay. So if you want a map from VB into VB, you must decide the image. Do you want to have the image in contravariant or in covariant component? If you want the image in covariant components, then you need a 2 times contravariant representation of the linear map. If you want, starting from covariant components of V, if you want the contravariant components of W, starting from contravariant components of the starting vector V, then you need a 1-time contravariant and 1-time covariant representation of the linear map. And if you want the covariant component for W, starting from the contravariant components of V, you use the previous matrix, but with inverted order of indices, or L. Then we are
done, no?
sorry. Yes, you're right. I did something wrong. Stupid. I wanted to do it. You know, this is what I wanted to tell now. And now, thanks. So, you know, I said something stupid. I wrote without thinking. You have the 2 times covariant. I was thinking something else. Okay, so you have the 2 times covariant representation for L. So let us repeat this another time, because this is also something very useful. You know, believe me, in the last 30 years, no, in the 4th, since I learned this theory, I used these concepts systematically. I did not write a single paper without using these concepts. I will come back to some aspects of our presentation of today. I think you need to hear this at least another time, but I will do it after we start studying equilibrium of continuous bodies, so that you see the possibility of application of our ideas. The possibility of applications are infinite. How these L's are transformed one into another, I made already some calculations. So I ask you to do the others, so you can reconstruct everything. By the way, you start with the basic representation. Okay? This is the representation which maps contravariant into contravariant. Okay. Then, when you need a 2 times covariant component of the linear map, because for some reason you want to write this formula. So you need the covector, which is the image of your linear map. Okay. Then the identification, which allows you to write WH equal GHL. Oh, sorry. GHLWL obviously tells you that LHJ is equal to what? It is equal to LJM GMH. It is enough that you transform this component. So you write that WH is equal to GHM WM. Then you write this like GHM LMJ VJ. Okay, and you discover that this is equal to LHJ. Because you have this equality and this equality. Okay. So you have this transformation from the one-time covariant representation for L into a 2 times covariant formula for L, representation for L. Okay, if instead you want L, H, J, the 2 times contravariant, starting from the, sorry, I must make up. So in order to lift one index, I use JMI. Okay. A trivial consistency observation I stopped writing before. If we want to write in this formalism the trivial relationship, now I need a consistency rule. If I take the index up and I transform it in an index up, Gij must be equal to delta ij. So when I represent GMN, the inner product, 2 times contravariant, like this. But this is also and this matrix is inverse to this matrix. Okay. However, look here. This, by definition, is Vn. And it is saturated with Vn. So what we discover? Of course, I can write W here. I don't need to use the same So I discovered the very useful formula for inner product. Look, this is the first time in my life in which I'm teaching these things at this speed. So I tell you my problems in deciding how to teach you these things. Either I was teaching these things much more slowly. I had a book written by a mathematician. I was teaching to physicists, and I taught this for, I think, 35 hours in a course of 250 hours. Okay, so I was doing everything in all small details, or I was teaching it to PhD students in a much quicker way. Okay, which I think was a disaster in a sense, because only few students who wanted to study these things on the book did understand really what I was telling them. Now I'm choosing a middle way, and please give me your feedback. Not only like Rizza now, who pretends to make a very clever face when I'm telling something. I thank you, by the way, Rizza, because otherwise my lecture could be really crazy. And Erden has to follow because I gave him the order. Okay, but please give me your feedback. If you are afraid, you can talk with Erden, with Alessandro, but I prefer if you give me your feedback, because I think it is very important to tailor. I will give this lecture in the next 12 years. It is not a lot of time, but it is, I mean, many students will be using this course, this class. So please give me your feedback. So why I'm telling you this now? Because I could have said to you this immediately, but I wanted to tell it now because it seems to me more natural. You know, when you have defined the rule of when you introduce the contravariant transformation of a covariant vector En, and when you have defined the inverse matrix of G in this way, this equality is natural. But if you need details, try to reason by yourself. Okay, and in case we will do some extra explanation about this. But what is important is that if you consider the transformation of covariant into contravariant components, you write this formula. If you consider the transformation from contravariant to covariant, you write this other formula. And you discover that inner product is easily represented by using contravariant components for one factor and covariant components for the other factor. Okay, and what is really interesting is that the inner product between V and W in every inner product. For every pair of vector is written with the standard rule, which is valid in an orthonormal as it is true in an orthonormal basis for Euclidean inner product. So VW, VB is equal to V1, W1 plus V2, W2 plus V3, W3. It is the sum of the products of homonymous, having the same name, components. However, one has to be contravariant, and the other has to be covariant component. Okay. So this is very interesting, and I repeat you that as I want to keep the rule VI equal GIJ VJ, you know, I want that GIJ 2 times contravariant, covariant, GHL 2 times contravariant. I want for the inner product to keep this structure when you have one index contravariant and one index covariant. So I want to transform a contravariant component into a contravariant component. This can be done only with delta ij. And when you look at this representation, the inner product between V and W in VB is equal to VI WI. Okay. But it is also equal to GLN VMWL. Because this is the tensor representing the components of the tensor inner product, one time contravariant, one time covariant, one time contravariant. And this equality is possible only if Gij is equal to the Kronecker delta. So as you can see, everything is kept at its place with this wonderful notation. Okay, we are a little bit tired. I said maybe many details, but I don't think too many. Now you can easily reconstruct the general rule. If I have L, I1, IN, J1, JH. Let us use K. Okay. And this is a K times contravariant. And then H times covariant tensor. The corresponding Cartesian tensor can have, for instance, you can decide that you want to lower one index. So you have LJ1, JH, JH plus 1, and you have I1, IK minus 1. How you are lowering IK index? Now you have learned how to do it. You saturate the index you want to lower with the suitable form of the matrix representing the inner product. So with the suitable components of inner product. In this way, you transform your initially k times contravariant, h times covariant into a k1 contravariant, h plus 1 covariant tensor, which is the same tensor, another representation of the other tensor, if you consider them as Cartesian tensors, and you identify, as we have done, covectors with vectors. I think it is wise if we stop here, because otherwise you will be too tired. I didn't stop enough times to keep talking now. Okay. Can I ask? Okay, let us stop the